hello. I think we can slowly start. It's about time, so hello. Здравствуйте, dzień dobry, dobry dzień. It won't be a scary session, for sure. No worries. It's just a mask, but it will go away soon. Maybe now, okay. So this session is a Lambda core hardcore. And yeah, you are welcome. About me, I look actually a little bit different. It's a photomate, okay? A little bit worse now. I am Jarek, wizard, developer. So I do write code, a lot of it. I delete, and I'm an architect. However, written like this above. And that's my tweet handle. Please follow me. I write sometimes things. My professional life is mostly associated with JVM, this sign. Although I actually code and have experience with a lot of languages, like those are my Pokemons. Okay, work for this company called Ingenious in Switzerland. We do stuff for financial institution, banks. We are hiring, we are looking for good people, really. So contact me if you think you are good. Okay. What we are going to talk today about, I think it's a little bit, let's say, loud. But okay, so first thing, if you came here to hear about lambdas, how they're internally handled by JVM, what's the guts below? That's a wrong presentation. It's not gonna be about it. It's totally different. It's, let's say, useless academic stuff. It's so useless that actually you might like it. And second, we'll be talking mostly about numbers. The thing that you think you know what it is, but it's not that easy, in fact. And then I will introduce something called lambda calculus. Who had heard about lambda calculus before? Couple of hands. So I'll show you this is a really funny thing to play with. And then you will be able to make fun of Haskell programmers. They will never scare you again, really. Okay? And I will show you that in Java. So if a lambda calculus, when you read about it, seems like, I don't get it. In Java, hopefully, who is a Java developer here? Yeah. So you will understand that you can play with this at home. So like explaining in a language that you in fact know. And we'll have some fun, of course. So, one thing, what you hear here will be simplified. First of all, because of the time. I don't have like 2 hours. I'm not a scientist, so I'm simplifying stuff. And I've studied mathematics. Sorry for that, but it was a long time ago. I studied mathematics because by the time I was choosing what to study, I was able to do that on Commodore 64. By the way, who had Commodore 64 here? You are too young, only one, 2 person, great. Commodore! Okay, so when I was able to do that stuff on Commodore, I realized there is nothing I could learn more studying informatics like computer science. What for? So by that time, my colleague on PC AT was able to do that stuff. So he had the same problem. There is nothing more advanced you can learn. So the thing we've chosen mathematics because we thought, everything else we already know. And the first lecture, while studying mathematics, I still remember it because the professor, the teacher, was showing us a proof that 1 doesn't equal to 0. Like all my life I never doubted. It was like kind of obvious, who is actually the end? No, he started from this point. Are we sure? So it took, I think, less than an hour to prove that 1 doesn't equal to 0. It is the proof that it would take me probably now a day to understand what was after so many years. And funny, first time in my life I've seen the proof of this, and first time in my life I started to doubt, actually. So, half done job. But nevertheless, I realized that mathematics is actually more fun than what we learn at the primary and secondary school. Okay, so because all that starts from the question, what is a number? And yeah, what kind of stupid question is that? Who can tell me what a number is? Explain me numbers. Don't using, yeah, and this is actually a problem. When we try to be precise what we are thinking about number, mathematicians try to formulate that in somehow, in a way that would be precise, would be correct. And it was hard. Let's think for a moment about a number like 2. Of course, I have like 2 things in my hands. I have 2 hands. Yeah, it's easy. I have 2 eyes. It's easy. So I need 2 things, and then it explains what the 2 is. And then there is a problem, like, oh, that's really, this is a coin, Polish zloty, and it has 2 on it. It instantly makes me a problem because this is a 1 coin. How can it be 2? And this is even worse. I have 2 coins, like local currency, hryvnia, and there's a problem. 5 hryvnia, 10 hryvnia. But I have 2 coins. Now this is like really, I'm confused, yeah? What is a number? Is there something like, can exist something without having real objects? What, like the representation? How can we think about it? So mathematicians thought about this problem and they tried to define a number not referring to anything that we have in a real world. Because real mathematician hates real world. This is boring, this is ugly, dirty. So for a moment we pretend there was nothing, like no Big Bang. There is just the world. Let's pretend universe was never created. There is just a void, nothing. Not this void in Java, but void, real. And let's pretend there was even no our supernatural creatures like flying spaghetti monsters that help us. Nothing. We have nothing. There is a void. And in this void, can we introduce the concept of numbers somehow? Is it possible? You have nothing. Yeah, that's a good question. And I won't make you hard for them. Mathematicians said, okay, we need to start with something. And they said, there exists something, let's pretend something exists, a set, a concept of set. You know what the set is? Like from the school. Yeah, you gather a group of elements, okay? So we have an idea. So we don't need any objects. We just have idea there are sets. Okay. In an empty world, can there be any set? Like you have no objects, like you have no bottle of water to put into the set. Can you have something that exists in a void and is a set? Show me, tell me. Yeah, empty set. What a genius idea is that? Like empty set doesn't need anything. So how cool? We had nothing, and now magically, actually mathematically, we had only a concept. Idea doesn't need reality. It's a concept of set, and then we created the first object, a set. Okay, it's an empty set. We can't do much with that. But there is a question now. Can we introduce something more in this empty space? Another set. Would that be possible? What would be the next thing that we can have? Not which set? Okay, the point is that you can have empty, yeah? Exactly, because in sets, you have to put some objects. Okay, either it's empty set or it has some object. We didn't have an object, but we just created one. An empty set. This is our object. We'll put that into the another set. And believe me, this is actually another set. They are not the same. So we have now 2 things. It is great. We had absolutely nothing, and now we have 2 things. Okay. And actually, there is a mathematical procedure how you can go with that up to infinity. Don't bother with that. We'll see more. But basically, there is like a procedure that if we have like those 2 elements, we can have third and fourth and so on. It's like this is like element, third element in our thing that actually represents, we can say that this first represents 0, this represents 1, this is a successor operation, and this represents 2, and it goes on like this. Look, this is a tree. Okay, And this is how actually the formal mathematics that you typically learn at school is built. You don't learn about it that much, but it's actually how our fundamentals were built, classical way. With a set theory led to numbers, and now, having a concept of set, we can, in a just empty universe, we can create numbers. And we can actually have operations like plus, then minus, and all this goes on, and actually it works. This is the mathematics that you typically know from school. You don't go that deep, typically, but it's there. Okay, why do we do that at all? So we do that for one thing, because mathematicians dreamed about, let's build our building blocks, like let's define our building blocks. What do we have in mathematics precisely? Create a mathematical precise language. What for? Because there was like 100 years ago, something like a holy grail of mathematics. It's if our building blocks are well defined, maybe we'll be able one day to create a formal procedure that will take any theorem, like someone will just think something out of the blue, like Pythagoras, Fermat, big theorem, and then there will be a formal procedure, deconstruct it to these building blocks, to these small blocks, and say it's true or it's false. So basically, mathematicians were working on the same thing as we now work in computer science. They tried to be useless. They were building a machine that would render them useless, exactly like each computer, like each software developer working on a machine learning right now, okay? Or artificial intelligence. So, okay, this actually worked, but there were some problems with this set theory. There is like famous problem, like let's consider the set of all sets that are no members of themselves. This okay, and then is the R member of R? Okay. Probably, I don't have much time to describe it, but there is a way to paraphrase it. In a city like Kyiv, there is a barber who shaves all the men who do not shave themselves, and only those who don't shave themselves. And now the question is, this is really the same question as above, does he shave himself? Because if yes, he cannot shave himself. The problem is that the statement this, it's neither true nor false. It's somehow like, and this is actually the paradox that led, okay, with set theory, we cannot prove that something is true or false because we have sentences that are neither of them. Actually, there was a correction to this set theory, to the building block. If we add something more, we get solution to this paradox. The problem is, like in set theory, like our first building blocks were quite elegant, and I would say everyone would understand them. Like, how we add sets and stuff like that. And to solve those paradoxes, mathematicians had to add very crazy axioms. Like, it's typically like you do a small project, you talk to a customer, and the first week you have a picture, you build architecture. And it was, for instance, this invoicing system. And now the customer and it's everything beautiful, seems to work, you have a picture in your mind, and then after 2 months, customer says, okay, and actually I wanted also document management. And this whole falls apart. Like you have to destroy your architecture, and because he says, okay, in a week, and then you are left with something ugly. The same happened to set theory. At the beginning it was elegant, after a couple of years it became ugly. More and more axioms, more crazy. Most of them, at the end, I wouldn't even be able to explain. Okay, so can we do something different? This guy, Alonzo Church, who has heard about him? Okay, cool. So this will be really, for those that haven't, this is like amazing story. I'm showing you something that you can follow later. This is amazing story, like a lot of stories. The guy had an idea. Maybe our building blocks are wrongly chosen. Let's take something else. Maybe not make a set the fundament of mathematics, make it a function, something fundamental. Yeah? Now, you know the problem, how a function? What is a function? From school. Yeah? Something that takes one element from one set and gives you back other elements from another set. Domain, codomain. And the problem is, so you need sets to have functions. That is not a solution. So he thought about functions. Let's talk about functions not talking about sets at all, forgetting about set. Function is something that takes something and returns something. And by the way, we only have function, so this function actually can take one function and return another function. Just this. We have functions that operate on functions and nothing else. Okay? This is what we basically call Lambda. Lambda is a function. Okay, this is not exactly the Lambda in Java, but there is like similarity. I will show you how to represent it. So Lambda is just a named function, let's say, actually the definition of a function. So let's go back to our empty universe. We have absolutely nothing. There was no Big Bang, no supernatural things to help us. We have nothing. But we have idea of function. Can we describe in a smart way a function that exists in a void, that you can describe it, it will be easy to understand what this function does, but not using any objects, sets or whatever. What kind of function would that be? Yeah. Yeah, identity. This is the greatest function of all. Like, function takes something, some x, and gives you back exactly the same. Does nothing, yeah, no operation. It's just, yeah, it's very fast, of course, very performant. You should do everything with identity functions, yeah? And so it takes a mouse, gives you back the same mouse. How cool. Takes other function, returns exactly the same function. So this is actually how we represent in Lambda calculus identity. Lambda means just, I start defining Lambda. Something that takes some x, and after the dot, it's written what I do. I just return this x, and this is identity. Okay, okay, this. So now, let's do that in Java, okay? First thing to do in Java is actually, I would have to define what a lambda is. I will make it for you easy. Functional interface. This will be an interface. I will call it lambda, okay? Starts like that. We'll have one function, which gives you back what? In this world, what? Sorry, I don't hear you. Okay, in this world we have only one thing. What? No, the world is void, but we only have one concept, and this concept is lambda. So we know that we have lambdas. The function will return lambda. This function will be called apply. What will it take? Lambda, yeah. What a great idea. Wow. Yeah, this is exactly how you represent Lambda calculus in Java. You can implement this interface. The implementation is basically a Lambda in a Lambda calculus like way of thinking. Okay, let's go further and sorry, just a moment. So I will start playing with that. Identity will be like that. I take x, return x. How cool, yeah? Then I print it. Okay, now the thing is, in this world we don't have println, but for sanity we just print what it is. Well, let's look at this. Probably something really stupid like this. Okay, system out println is something I'm only using to debug, but now I will show you that this thing really works, because if I have identity, what can I do? I can apply it with something. It has apply. What can I use here? I already helped you. The only thing I have is identity. Oh, this is boring. But you will see that it works in just a second. Yeah, this is the same number. So we see we get the same stuff. Okay, well, doesn't really look impressive at this moment. Okay, it's not yet. This is not the thing I wanted to show. Let's go with that. So lambda, let's go back to definition, is something takes, we define that we will have some kind of variable, argument. We name it x. By the way, name doesn't matter. By the way, lambdas only have always one argument. You never have two of them. Like the basic definition is like function of one argument, which by the way, this argument must be a lambda. And then we'll have some expression. So for instance, this is like, I take x and then I add x to x, or I take x. This is like a function definition. You know this from school. The problem is that we don't have plus, we don't have sinus yet, because this is empty world. And by the way, this is not even numbers, so this is a function. What would, in that case, sinus mean, yeah? Oh, this is stupid, yeah? But nevertheless, the concept. We have only one thing that we can use in our empty world. Define lambdas, and inside these definitions, we can use application. So it is like we have a Java, we can create interfaces in Java, we can create classes, you can implement those interfaces, but we cannot create, in fact, methods. We cannot use anything like from Java standard library, no, and we cannot even use int whatever as a primitive. Let's think about Java without anything. You have just a language, and actually only a very small subset of the language that lets you define lambdas. Can we actually do something with this very limited Java with nothing? And that's what I'm going to present you, because this, yeah. Let's go back, not to Java, but to the definition. Okay, we had identity function. Can we create something more? Because it was easy with sets. We could have created set of a set inside. What can we do with lambdas? It is not as easy with sets, so I won't bother you with that. But let's look at this lambda. Slowly. Take some x, and after the dot, what I return? I return a lambda that takes y and returns y. So this is, by the way, identity. So this is a lambda that takes some x and gives you back identity. What it means that this x is totally ignored. Whatever you give there, it will return you identity. Is it different than normal identity? Actually, this I will show you. For instance, let's say for a moment we borrow some objects from other universe, just for a moment. They don't belong to us because we only have lambda. So we have this lambda and we have a trumpet and tomato. In the first step, in place of x, I take like this dot, I apply. For a place of x, I put the trumpet and put wherever here x is, I use the trumpet. Actually, it's nowhere there. So I land with something like lambda from y, gives you back y, and takes a tomato. It's like a first step of application. I just did one step. And then it takes y, so in place of y, I put tomato. I end with tomato. Oh, how cool. Then you can define actually a little bit different lambda, like this. I take some x, and after that, I will return you lambda that takes some y and returns x, like the first one. Now, if you try with this, with trumpet and tomato, you will see that I take a trumpet for an x, and then I return something where trumpet is in place of x. So here, you see? And this function then will take tomato, but will completely ignore it and give you back a trumpet. So actually, I presented you two other lambdas, just the concept. They actually don't need any trumpet or tomatoes. We just give them back. And this is even more. For instance, we can create lambda that takes some x, and then returns you lambda that takes some y, and it returns x applied with y. Whoa. And I won't do that, because if you apply tomato to trumpet, you will destroy the trumpet, and we have to give it back to other universe. We are not cheating. Okay, let's start with Java, because it's all about, yeah. So, if I do it in Java, we have this identity, cool, why not? So what next can we have? So I will do Java with nothing. With one small exception. I'm not cheating. There is no cheats here. It all works, but I use my package. What is my package? It's only for displaying. So if you do in your computer plus operations on integer, you actually manipulate some bits, but you don't look at those bits because it just basically says you nothing. You want to print them as a number. So here I'm manipulating on lambdas, but instead of printing this stupid hash code of object, I want you to show how this lambda look like. So I have created a special package that basically takes some lambda and presents you how it looks like. By the way, it's mathematically proven it cannot work. But I don't worry with that. I use some magic. So I take identity and it presented me from Java to mathematical description. This is identity. This is how it looks like. Okay, so now I can do more stuff. I can create this funny lambda. This is exactly the one that takes some x and returns you this y, a lambda that takes y and returns again the same x. So one of those that you've seen just before. And I can present them. Yep. Let's see that it works. Yeah, you see it works. Okay, this is just a proof that we can play with that. And now I will present this lambda. By the way, it's exactly the same as above. And what is important, I just gave it a name as true. But important here thing is that actually, in place of true, I could use this funny, because in lambdas, only the shape inside is important, not how it's named. So I could actually here use the funny, because they have exactly the same shape, but there is a reason why I called it true, because then I call this false, and I can print it. Okay, I won't now do that because it's slow. I have a Maven behind that compiles it, but I will create you this lambda. It is called end, and it looks scary for a moment. And I can even print it. Just, yeah. So we just see a couple of lambdas. This is true, this is false, and this is end. By the way, it could be printed with X and Y, but this is like how, because the names of the variables doesn't matter, as in Java. It just, here could be X, and then I would need X. But I present it in the same way as you see that in Wikipedia, for instance. This is like convention used by mathematicians. So now let's do something like this. I take end lambda, make it more visible, just on the, maybe, yeah, oh, this is like this, just a moment, yeah. It's now more on the screen. I take this end lambda, this is just lambda, and apply it first with false, then I get some other lambda, then I play with this true, and I get some other lambda, which I put into result, and then I simply display it. Okay? And what would that be? This is result is something like this, and we know this. This is what we called false. So actually what we did here is that we've proven that end with a false and a true would give us a false. And by the way, I can also play with like this, like z, actually it can be small z, like gives you, oh sorry, too much Scala, gives you some t, that gives you a t, no, actually gives you z. This has the same shape as a true, so now our result should look like a true. You see, it works. This is the whole thing, and by the way, we now go very quickly for like, lambda or, and I won't waste time on this, but believe me, this works as well. Or, and I can have result of or, and I can print this result, and I can have even more like lambda that is called not. So I take something and I negate it. Sorry, like I will just show you on the screen. So we'll present not from false at the end. Yeah. So let's see that. This should work. So we have or operation, then in a second or true and false gave us true, not false gave us true actually. So it's cool. Having nothing, we've created boolean logic. Having only Java with nothing and actually lambda calculus only with a concept of lambda. This is awesome, believe me. Okay, but is it all we can do? Of course not. There wouldn't be this presentation if it was all. We can go farther. Yeah, and this step further is, what about numbers? We started with numbers. Can we represent, I've shown you how to represent true and false. By the way, this is one of the conventions, the most popular one. You could actually, there are like infinite ways to define true and false and or that you do work. Those are like the simplest ones, but that we know so far. But let's now define something like this. 0 is this. By the way, have you seen this lambda before? At this presentation. One thing, name of arguments do not matter. This is a false, so actually, whenever you refer to C programmers, where 0 is false, they were right. Lambda calculus says the same. Okay, 0 is false. So we use the same lambda to represent 0 as we used to represent false. Okay, this is the most popular convention. And then we define one like this. And then we can even print it. So I can print this, and then I have two numbers. You see, basically, you will see in a moment how it's done. I will just do some. And I have something called successor. Oh, it looks ugly. But OK, cool that I still remember how to use it. So I will use successor from, I will print successor operation. So we can, really, I have one concept. Only lambda. This represents operation and numbers. How awesome. With one thing. Now I can present even successor from 10. And by the way, I have here some utility package. There is no magic there. I just create, just not to repeat myself so many times printing some f's, I have something that takes Java integer and makes you lambda representing this integer. Just to show that it works, to not spend much time typing FFF. So basically, the point is how we represent numbers. We take two lambdas and we apply so many times the first one as the numbers we represent. So 0 is we never apply f with x, 1 is we apply once, 2 we just f at x with apply 1 against. Successor is like this, and we, for instance, see that successor from 10, it should be 11 of f's there. You can count them for me, but okay, cool. You see that, for instance, successor of 1 is 2. Okay. And having that, if we have successor, there is actually easy to create plus operation, which internally uses something like successor, and then you can actually, now what I'm doing, instead of putting this FFFFF, I have this from integer, which creates me this lambda. I will show you how it looks, because I will present how its internal abstraction of A looking like, how its external abstraction of B looking like, and then we'll present the sum of those things. How cool. Yep. And then blah, blah. That's it. This is... Now you see that I took some 6 f's, 7 f's, and I got a result of something that has 13 of them. It really works. I can even, you know what? Don't waste time. I can tell you that even the operation like multiplication works. So you have multiplication here, and the same, maybe let's check it. We'll multiply A with B. So at the end you will see, oh, A plus B is 13, but if we multiply it, we get so many things. Again, we only have one concept, lambda. It's so powerful. You can have everything with that. You don't need integers. Nothing like this. Okay? But now comes the question. Can we only do these simple things like straightforward? Plus, if you, for a moment, think about it, there was actually a problem in lambda calculus, how to do subtraction, how to make a step back. And actually there is a funny story behind it. I don't have a time to show you, but explain it. But it was a problem that was solved by, let's say, one of the students, I think, or I don't know if he was really a student or just working together with church. And that's how we define decrementation. It is ugly, yeah? It's really like this. And this is something I wouldn't be able to do at 2 a.m. in the morning, but actually it works. So we can display it, and we can actually use it. For instance, we can decrement 9 number that I defined before and see that it works. Okay? So I present 9, and then I decrement it, and it should be there. Yep. So let's just take a look that it works, because we are about to start something amazing. So we can decrement. You see there is 1 f less. You can count it. If you don't trust me, make a photo and count it. It really works. But now the fun starts. So we can have, of course, subtraction. I won't cover it much. It just works. Yeah, believe me. But the fun start things here. Like, I can have something. Okay, I will do small thing. I will put it on top of the screen. If lambda, let's forget about. If lambda, what crazy thing I'm going to introduce here? By the way, from the shape you should see something. This is a lambda that takes some c and takes some argument, we call it c, then some argument which is t and some argument which is f. And c is a condition. True is something you do when the condition is true. F is something you do when condition is false. This lambda doesn't represent number, doesn't represent simple arithmetic operation. It represents if expression. So concept from algorithms, we went a step farther. Now it's amazing step what we can do with that. We can, for instance, define this condition. By the way, again, this boolean false alpha, this is my boolean, and true alpha, those are simple definitions of true and false as I used before. I just don't want to repeat myself and make it more readable for you. Those are those variables as on the previous slides. And now, for instance, this operation is less than equal. This is a condition. So is 0 and less than equal are lambdas that I can use in place of C, okay, as a condition. And now the magic starts. This is very nasty lambda because it says something, autocall. I take x and apply with itself. So I call it very rude operation. It's like a guy, do it to yourself, like, you know. It's like, and then we have, using this, however, we can create something amazing. Who knows what this is? This has a special name. Y combinator, exactly the Y name is used. Why it's very special? Because, let's look at this lambda. By the way, it's a little bit horrible. I will analyze it. We still have a little bit of time. Whoa, this is horrible stuff that we are having here, like, okay. And then probably like this. Let me see if it compiles, because typically I forget a couple of, I need one more. Just a moment, I need one more. Now it would it compile? Yes, so let's think, what is this? Like, ignore this R parameter. There is some operation that takes an n, and I can tell you n is a number. Okay? Maybe I will use this. N is a number. Then I use some f. If the number, with a condition, if the number was 0, then I return 1. It's here, okay? Return 1. However, if it's not 0, then I multiply n with, let's say, R represents the same operation, so it's like we'll go back and apply the same function with something like n minus 1, predecessor. It's like decrementation. So you do something that is 1 for 0, or you call recursively the same function, but multiplying n with function, but n minus 1. What is this? Factorial, yeah. And the point is, why do we do this crazy stuff? Because if you have a function factorial, inside of a function that you call factorial, you can call factorial again. You can use the name factorial. Well, in lambdas, it's not that easy. But because let's pretend this is factorial. Would we be able to use the factorial something? No, because in this moment, factorial is not yet defined. You can use recursion with functions, but not with variable definitions. That's the problem. So in Lambda calculus, exactly is the same problem, and they created something like, why is a magic thing that takes a function and makes it recursive, really? So now I will preview, sorry, what's happened to my keyboard? It should be assisting me. Factorial is simply, I take this G and make it really recursive, and now a proof of that. Because let's start with 3. I will use this factorial from 3, and we'll just present it, we'll give a result, blah, blah. That's easy, yeah, and then we'll display that. And by the way, for convenience, I will also present you, I have special function called toInteger, which basically calculates how many times I've seen end. So that, at the end of the day, you are able to see if the calculation was correct. So, you see, this is, I had factorial from 3 and it was 6, okay? This is this 3 number. You have 3 times f's. Okay, is it so amazing? It would be if I was use here something like 7. You have to see that to believe. Okay? And somewhere at the end of those f's is 5040 f's. You can count them. This is really working. So what I've shown you with this is really in an empty world, we are able to create a concept, all the concepts we need actually in processing, not only mathematics, arithmetics. Actually, we can build with Lambda all our algorithms. And by the way, it's proven. Turing actually proven that in 1947 that Lambda calculus and Turing machine are equivalent. Whatever you can do on Turing machine, you can do with Lambda calculus. It's great. So it's purely functional programming. And it has some consequences, which are funny, because maybe now we have this ultimate theory. We can, in an elegant way, represent anything, and we can solve our problem. We'll go back to this problem. So, what was the problem, actually? If we have mathematical theorem, what it means, for some condition, it gives me some statement. We can represent if in Lambda calculus. We can represent conditions. We can represent statements. Would it be just nice to represent our mathematical theorem with this? And it's possible. We can basically take any mathematical theorem and represent it in this way. And then what we do? We just fire it and see the result. Is it true or false? Wouldn't it be that awesome? Yeah? Actually, for some of the theorems, you can do that. And there are some of them that you can do that, write them in a Lambda calculus, and check the result, is it true or false. You don't need mathematicians to prove. There is, however, a problem. The problem is, you've already seen this nasty Lambda called autocall, that you do it to yourself, dude. Then we can use it to create something even more nasty, which is called omega, which I take autocall and I play with autocall again. Yeah, this is really bad stuff. Okay, just a moment. This is just short thing. Now, I don't do much, I just fire it. And what would I get? Stack overflow. That's the problem. In fact, any more complex theorem that you analyze will sooner or later explode on Stack Overflow. You cannot, with Lambda, analyze other Lambdas because they could be infinite, and you will get in the endless loop. That's the problem. And actually, in 1946, Church, the guy that invented this theory, proven, okay, there is no Lambda that can take other Lambda and, for instance, can tell you, is it equal to truth? Like, take this mathematical theorem and say, is it truth? No. Nothing like this exists. This is a horrible thing because it means the problem is not solved. Nevertheless, some people on Stack Overflow, they didn't have like mathematical background, and they still are proving this thing. It's a little bit long story because they are implementing the Lambda equivalence in C#. No one told them that it's impossible, and no one would told them because who knows, maybe they will find out. Yeah, that's great. So we'll see how it proceeds. Yeah. Okay. So there is now a problem. So we've just created beautiful theory, and we've seen that it still doesn't solve all our problems. So maybe the Lambda wasn't the good building blocks. Set weren't good. Maybe Lambda as well. Maybe there is something better. And now we have a really nasty guy known as Kurt Gödel, who actually proven that whatever you choose, no matter how smart you are, if your theory, formal theory, how you build mathematics, it must be at least having arithmetics and some statements. They will have some statements that are true, but you cannot prove them. There's actually more to that, but basically it means no matter what you choose, you will always have holes in you, and you will never have something like generic problem solver, that you have automate that will create, at least in our universe, that will just solve all your mathematical problems. Sorry. Okay, let's go to the end, a summary. Lambda calculus can be done in Java. If you couldn't follow this, it's like you can actually, will later give you a GitHub with all of this, so you can literally take Wikipedia definitions and try them at home with Java. It really works. Yeah. And there is, however, I avoided a lot of problems. For instance, in Lambda calculus, there is always the problem eager, lazy applications. Actually, if I created this like this, lazy X, I would be able to do something more, but there would be other complications. Actually, there is not just Lambda calculus. What I've shown is something like untyped Lambda calculus, which is crazy because if you have plus operation, you can apply plus with 2 and 3, but you can apply plus with multiplication and not. What does it even mean? Actually, some of those terms are useful. This is really powerful thing, like any dynamic languages. But in order to make some, let's say, sanity to that, scientists created simply typed Lambda calculus, and it goes better. And actually, out of that, we have functional languages. This is how functional languages like Haskell, SML, Occam, this is the building block. It started from Lambda calculus. Actually, Lambda calculus definitions, as I've shown you before, you write them exactly the same way. You don't need this interface, whatever. You just, instead of Lambda, you use a backslash, and you have this in Haskell. It's really, in Haskell, it's natural thing. And the rest is just syntax sugar to make it easier for you. So, and this is actually, for me, what is important, that you can do, this is equivalent. Whatever you can do on a computer, you can do purely functional way. Maybe with Lambda calculus, it's not the most efficient way. There are smarter ways, but you can do purely functional, because even with this very limited language, like Java, with nothing, you could do everything. It's proven. So this is a science. There is, like, if your colleagues have, like functional programming is limited, you can only use it like in some areas. No, you can use it for absolutely everything. Pure functional programming, not just any. Yeah, this is cool. And by the way, we are at the end. Remember that there is this application, and you can choose. It was awesome. I was amazing. Whatever. Those stars on top are obvious. Yeah, I hope. Yeah, and then. This is end, dziękuję. So if you want to know more, actually Wikipedia on this topic is really cool. It's really good enough to try it. There is a really great C# blog, but you know that C# is just pure copy, like poor copy of Java, so you can read it and understand it easily. And there is like, this is like, 10 times more what I've presented, or even 20 times more on this Dixon blog. There is like book that inspires me to such things, Emperor's New Mind by Roger Penrose. By the way, it only mentions Lambda calculus, but it describes quite well like Turing machine with nothing. Really, it presents some crazy stuff about. If you want to, playing with Lambda is easy. Representing that, it's hard. So you have this package on a GitHub. It's really, by the way, it's proven mathematically because of actually the same problem like exploding lambdas. It cannot work, but for simple lambdas it would work. It's called Bedlam, and it basically will do this nice printing for you of lambda. So you can play and see what you do in Java. And that's it. Thank you. Dziękuję. Questions? Are there any questions?